Good day, class, and welcome to another lesson in organic chemistry. In our previous lesson, we treated aliphatic hydrocarbons, and we defined hydrocarbons as compounds containing carbon and hydrogen only. And we said the aliphatic hydrocarbons include alkanes, and alkynes. We went into detailed treatment of their physical properties, and we did their reactions. We also looked into their preparations. How could these aliphatic hydrocarbons be prepared? We looked at distinguishing them from each other. In our lesson for today, we are going to be looking at aromatic hydrocarbon, which is benzene. The formula or structure of benzene shows that it is an unsaturated hydrocarbon. As such, this is how the formula of benzene looks like. This is it. As you can see, me drawing on your screen. This is the structure of benzene. All these as such. There on your screen, you can see the structure of benzene. Unlike alkenes and alkynes, it does not readily undergo their addition reactions because it is more stable than alkenes and alkynes. What we mean here is benzene is more stable than alkenes and alkynes. Let's look at the structure of alkenes. Let's take, for example, ethene. I take, for example, an alkyne. Let's take ethyne. You see that alkenes and alkynes undergo addition reactions to obtain an alkane structure, a saturated structure. Meanwhile, benzene doesn't undergo this reaction. To account for the different properties of benzene, it is proposed by the Kekulé that benzene has a ring structure with alternate carbon atoms joined by double bonds. And you can see them. You can see how the alternate carbon atoms have been joined by double bonds. This structure was proposed by Kekulé. And this benzene structure is otherwise known as the Kekulé structure. Right now, we're going to be looking at the limitations of the Kekulé structure. Limitations here is also looked at or called the disadvantages. Now, like I said, we'll be looking at the limitations or disadvantages of the Kekulé structure. A disubstituted benzene should produce two isomers. We say a disubstituted benzene should produce two isomers, one trans and the other cis. This does not happen when benzene undergoes disubstitutions. The second limitation is benzene should undergo addition reaction structures of alkenes. That is, according to Kekulé, benzene should undergo addition reactions, which is the reactions that alkenes and alkynes undergo. These addition reactions of alkenes do not take place in benzene. The third limitation, the carbon-to-carbon length in benzene should be either the same in alkenes or alkynes. This is not true. The actual carbon-to-carbon length of benzene is the same irrespective of double or single bonds. It is shorter than carbon-to-carbon length in alkenes, but longer than carbon-to-carbon length in alkynes, which means that the bond length in benzene, as such, whether a double bond or not, all this bond length from here to here are the same, irrespective of double bonds. And we said that this double bond is shorter compared to the bond length in alkenes, but this bond length is longer compared to the bond length in alkynes. What we mean here is the bond length in benzene is greater than the bond length in alkenes. This is the formula of alkenes, CnH2n, and the bond length is less than the bond length in alkynes. The formula of alkynes is CnH2n minus 2. Okay. The enthalpy of hydration, that is, the enthalpy of hydrogenation of cyclohexene containing one carbon-to-carbon double bond, is minus 120.5 kilojoules per mole. What we are illustrating here is this. We say that the enthalpy of hydrogenation, that is, hydrogenation is the addition of hydrogen, that you can recall from our previous lessons. So we say that the addition of hydrogen, which is hydrogenation of cyclohexene, this is the structure of cyclohexene, as you can see. This is the structure of cyclohexene, which has a single double bond. We said that when it undergoes hydrogenation, that is enthalpy of hydrogenation, its enthalpy of hydrogenation is minus 120.5 kilojoules per mole. And when this cyclohexene undergoes hydrogenation, it gives us cyclohexane, whose enthalpy equals whose enthalpy equals minus 120.5 kilojoules per mole. Okay. If the Kekulé structure is true, then the enthalpy of hydrogenation of benzene should be, that is, it should be 120.5 times 3, which will give us 361.5 kilojoules. What we mean here is, if the Kekulé structure is true, then we should have this. We should otherwise have this. That is 3 times 102.5, which is going to give us 361.5. Okay. What we're trying to say here is this. Since the benzene structure has 3 double bonds, that is this, if the Keku structure is true, this 102.5 kilojoules per mole, which is the enthalpy of hydrogenation of cyclobenzene, will be multiplied by 3. But here, that is not the case. The experimentally determined value of the hydrogenation of benzene is 208.4 kilojoules per mole. I repeat, the experimentally determined value of the hydrogenation of benzene is 208.4 kilojoules per mole. This means the actual molecule of benzene is therefore more stable than a Keku formula by 153.1 kilojoules, which means that the actual structure or molecule of benzene is more stable than the structure of Keku, because according to Keku, the enthalpy of hydrogenation of the benzene structure will be 361.5, but the actual enthalpy of hydrogenation of benzene is 208.4, which means that this actual benzene structure is far more stable than the Keku structure. It is stable than the Keku structure by 158.1 kilojoules. That is 361.5 kilojoules. 361.5 kilojoules minus 208.4 kilojoules per mole is going to give us 153.1 kilojoules per mole. This is how stable the actual benzene structure is. Okay. This difference is known as the delocalization, stabilization, or resonance energy. That is this difference, the difference of 153.1 kilojoules is known as the resonance, decolorization, or stabilization energy. That is, this is the delocalization energy. Delocalization energy or stabilization energy or the resonance energy of benzene. The structure of benzene is nowadays written as, the structure of benzene is nowadays written as this. The structure of benzene is nowadays written as such, like you can see on your screen, where O, that is this, where O indicates delocalized pi electrons. O indicates delocalized. It indicates delocalized pi electrons. O indicates delocalized pi electrons. The carbon atoms in benzene are linked by sigma bonds. The pi orbitals overlap to form a delocalized pi system. The delocalized pi bonds give the ring a high electron density. Now, Next thing we are going to be looking at is the naming of aromatic compounds. Like you can see, like we earlier said, that now we are going to be looking at the naming of aromatic compounds. For example, the first compound you see there, a methyl group is being attached on the first carbon of benzene. That compound there is known as methylbenzene. Methylbenzene is otherwise known as toluene. Also, you see that the next compound there is chlorobenzene, where a chlorine atom is attached on the benzene ring. The next is phenyl group, where you have a benzene group with a stroke attached to it, which means that stroke could be attached to any other compound. It is a phenyl group. You have the benzoic acid as the next compound. The next compound is phenylamine, where an amine group is attached on the benzene ring. We have nitrobenzene, and also the next compound there is sodium benzoate. And that is it. The next we'll be looking at is some examples of disubstituted benzene. Like you can see on your screen, the first example of a disubstituted benzene is 3-chlorobenzoic acid. The next is 4-nitrophenol. And the last one there is 4-bromophenylamine. Okay. The next thing we're going to be looking at is sources or preparation of benzene. How can we obtain benzene? Sources or preparation of benzene. First one there is decarboxylation. The first there is decarboxylation. Okay, decarboxylation, like we earlier saw, is the removal of carbon dioxide by heating sodium salt of a carboxylic acid with soda lime or sodium hydroxide. Like you can see there, the reactions. First, there we have sodium benzoate being reacted with sodium hydroxide and is fused with heat is going to give us benzene and sodium carbonate. The next we'll be looking at is polymerization. Polymerization, when benzene is heated in the presence of a complex nickel catalyst, it is polymerized. We say when benzene is heated in the presence of a complex nickel catalyst, it polymerizes to yield benzene. Like you can see there, that is ethyne being polymerized in the presence of complex nickel catalyst and heat. It's going to yield a benzene structure. The next method there is by destructive distillation of coal. This comes out when the coal tar, we say by destructive distillation of coal, this comes out with the coal tar, pushing which must further be distilled to obtain benzene. Say this comes out, that is benzene, comes out with the coal tar, pushing which must further be distilled to obtain benzene. The next there is by reforming of alkenes in the gas oil portion of petroleum. That is by reforming of alkenes in the gas oil portion of petroleum. Next thing there we're looking at is the reactions of benzene. In their boiling points and solubility, aromatic hydrocarbons are typical of non-polar molecules. The available delocalized pi electrons of the benzene ring attract mostly electrophilic reagents. Hence, the reactions of the benzene ring are characterized by electrophilic substitution. Even though benzene also undergoes few electrophilic addition reactions. The first type of reaction of benzene we'll be looking at there is their substitution reactions. Due to the delocalized pi electrons in the benzene ring, substitution reactions of benzene are electrophilic. The electrophile, which is, like you can see there, X plus represents an electrophile. The electrophile attacks the pi bonds in the benzene ring. A reaction with an electrophile is illustrated as, like you can see on your screen, that's a reaction of an electrophile indicated there. When the electrophile is attached to the carbon bond, when the electrophile is attached to the carbon atom, its positive charge is distributed over the 5 remaining carbon atoms. The electrophilic substitution reactions of benzene include a nitration, that is one of the electrophilic. Nitration is one of the electrophilic substitution reactions of benzene. In nitration, a mixture of concentrated nitric and sulfuric acid is called a nitrating mixture. The hydroxy group reacts with a portion, that is a proton, from the concentrated sulfuric acid, which is distributed as such. Like you could see, sulfuric acid being hydrolyzed to give us a hydrogen ion and sulfite ion. And this hydroxide ion further reacts with hydrogen to produce water. Nitrogen ion, that's nitronium ion, is called the nitrile cation or nitronium ion. It is the nitronium ion which attacks the pi electrons. It is the nitronium ion which attacks the pi electrons of the benzene ring to effect the electrophilic substitution. The reaction of concentrated sulfuric acid and nitric acid to produce nitronium ion is nitric acid plus nitronium ion to yield a nitronium ion plus water and sulfide ion. The concentrated sulfuric acid acts as a catalyst and a dehydrating agent. The nitration of benzene with nitrating mixture takes place between 55 to 60 degrees Celsius. That's the mechanism of the reaction, like you see there. Now you can see that is the mechanism. The next one we'll be looking at is sulfonation. But before looking at sulfonation, realize that at higher temperature, further nitration takes place to produce di or tri-substituted benzene. The next type of reaction we'll be looking at is sulfonation. And benzene reacts with concentrated sulfuric acid between 35 to 50 degrees Celsius to form benzene sulfonic acid. The reaction involves the breakup of the acid, that is as such, like you can see on your screen. That's the polarity of sulfur trioxide. That's the polarity of sulfite ion. The positive charge on the sulfide in sulfur trioxide makes an electrophilic attack on the pi electrons of the benzene ring. This is what we mean here. This makes a positive attack, makes an electrophilic attack on the pi electrons of the benzene ring to give us benzene sulfonic acid. The next thing we'll be looking at is halogenation. That is the mechanism of sulfonation. Halogenation. Benzene reacts with halogens. Benzene reacts with halogens in the absence of sunlight to avoid free radical addition. The reaction takes place in the presence of a halogen carrier as a catalyst and heat. That is, the reaction of halogenation of the benzene ring takes place in the presence of a halogen carrier. The halogen carrier acts as a catalyst and heat. The halogen carrier is a Lewis acid, that is electron deficient, and polarizes the halogen molecule. The halogen carrier may be a metal or its chloride, bromide, or iodide. For example, iron is a halogen carrier. Aluminium is a halogen carrier. Another example of a halogen carrier is aluminium trichloride and iron trichloride. Example, we'll be looking at the chlorination of benzene. It takes place as follows, where the chlorine atom is being polarized by iron trichloride in the presence of heat to give us tetrachloroferrate complex and chloride ion, which is the electrophile. The second stage there is the benzene ring reacting with the chloride electrophile, and this reaction, this step here is a slow step because it's the rate determining step to give us that. And we have it again at the first stage in the presence of heat, where the complex of tetrachloroferrate is being reacting to give us chlorobenzene and hydrochloric acid plus our halogen carrier, which is a iron trichloride. The next is Friedel-Crafts reactions. Friedel-Crafts reactions involves the substitution of a hydrogen atom by either alkyl groups of halogenoalkanes or carbonium of alkenes, that's a carbonium ion of alkenes, or acyl groups of acid chlorides and acid anhydrides. The first one we'll be looking at is the alkyl groups of halogenoalkanes. Alkyl groups of halogenoalkanes. Halogenoalkanes react with benzene in the presence of halogen carriers as catalyst. The catalyst induces greater polarity on the halogenoalkane. That is, the catalyst produces a greater polarity on the halogenoalkane. Like you can see there. That is a reaction, that's halogenation, under Friedel-Crafts reaction using alkyl groups of halogenoalkanes. The next is carbonium ions of alkenes. Carbonium ions of alkenes. The alkylation can also be achieved. The alkylation can also be achieved using an alkene with phosphoric acid as a catalyst. The alkene is converted into a carbonium ion. You see the alkene is converted into a carbonium ion, as you can see. The carbonium ion later makes an electrophilic substitution. You see the carbonium ion later makes an electrophilic substitution. Later makes an electrophilic substitution as such. You see it on your screen, where the carbonium ion is being reacted with phosphonium ion to give us a ethyl benzene. Like you see there, that's our ethyl benzene. Okay, the third one we'll be looking at is acylation of benzene. Acylation of benzene, that is addition of acyl groups from acid chlorides, is also catalyzed by hydrogen carriers. For example, acid chlorides. Let's look at the example of acid chloride. That's an acid chloride reacting with the benzene ring in the presence of a halogen carrier, aluminum trichloride, to yield us phenylethanone. Next we have there is an acid anhydride, which is reacting with benzene to yield us another benzene ethanol. The next reaction we'll be looking at is addition reactions of the benzene ring, and the first addition reaction there is hydrogenation. A mixture of hydrogen and benzene, favor when passed over nickel at 150 degrees Celsius reacts to produce cyclohexane. That is a mixture of hydrogen and benzene vapor when passed over nickel at 150 degrees Celsius reacts to produce cyclohexane. Like you can see there, that's a cyclohexane. And the next reaction will be halogenation. Both chlorine and bromine are added to benzene in the presence of ultraviolet light to produce hexachlorocyclohexane. The reaction is a free radical addition reaction, and the attacking reagent is a free radical resulting from homolytic fission. Now you can see there, benzene reacting with 3 molecules of chlorine in the presence of light to yield 1, 2, 3, 4, 5, 6 hexachlorocyclohexane. Hexachloro indicating that there are 6 chlorine atoms attached on each carbon, on the 6 carbon atoms of the benzene ring, which results now to give us a cyclohexane, which is a saturated compound. We've come to the end of our lesson for today, and in our next lesson we'll be looking at methylbenzene.